consider a simple electric circuit like this circuit. You have a battery and you have a resistor. This resistor represents a light bulb or any appliance that functions using electric power. Usually, we just care about the resistance. We don't care about the other details of the appliances in the circuit, because the resistance will determine the current in the circuit. So suppose you have this circuit, you have volt difference V, you have resistance R, you have current I. Now we need to learn about the electric power. As charges move from higher potential to lower potential, there will be a drop in the potential energy. We can calculate that. So the power, which is the energy per unit time, can be calculated from this equation, dq by dt, which is the electric current multiplied by the change in voltage, delta V. So dq by dt is I. Okay. So now we know that delta Q, delta V is energy. Divide energy, potential energy by time, you get power. You get power. So power is equal to I delta V. So you need the current I multiplied by the voltage drop between C and D in order to calculate the electric power. We may use Ohm's law. We know that from Ohm's law, delta V equals IR. So we can substitute for delta V here, IR multiplied by I, so it is I squared R. Or we may substitute for I as delta V divided by R, so the power is equal to delta V squared over R. These equations are identical. You can calculate the electric power from the product I delta V, or the product I squared R, or delta V squared divided by R. Power is measured in watts. When we multiply power by time, you get energy. So you divide energy by time, you get power, or multiply power by time to get energy. Therefore, we may have a new unit for energy, which is kilowatt hour. Kilowatt hour. Kilowatt means 1,000 watt, and 1 hour means 3,600 seconds. So 1 kilowatt hour is equivalent to 3.6 by 10 to the power 6 watt second. Watt second is a joule in the SI unit. Okay, so 1 kilowatt hour is a unit of energy, and it is equivalent to 3.6 million joules. This is the unit that the electric company uses when they charge us for the consumption of electric power at our homes. They use the 1 kilowatt hour unit, and their pricing is based on the kilowatt hour. A voltage delta V is applied across the ends of a nichrome heater wire having a cross-sectional area A and length L. The same voltage is applied across the end of a second nichrome heater wire having a cross-sectional area A and length 2L. Which wire gets hotter? So here it's gets hotter when the current is greater, and this would be the case when the resistance is less, and the resistance is less means the wire is shorter. So the shorter wire will have smaller resistance and therefore higher current, and higher current will create more heat. In this case, we have two resistors connected in parallel to the same voltage source. Rank the currents at points A through F from largest to smallest. The current going through A and B is the same. The current going through C and D is the same. The current going through E and F is the same. So the current coming from the battery at this point here will split. Part will go through this line, the other part will go through this line. So the current between A and B will be the highest. Okay. And since we have higher power here, this means we have higher current here. So the highest current would be going this way between A and B. It would be followed by the current going through the resistor here. And then the last one would be this one. So this would be the answer. The diameter of wire A is greater than the diameter of wire B, but their lengths and resistivities are identical. For a given voltage difference across the ends, what is the relationship between PA and PB, the dissipated power for wires A and B? From the resistivity law, we know that the resistance is inversely proportional with the cross-sectional area. So in this case, the dissipated power for wires A and B through A, it would be more power than B. Example, a circuit provides a maximum current of 20 ampere at an operating voltage of 120 volts. How many 75 watt bulbs can operate with this voltage source? Then at a rate of 12 cents per kilowatt hour, how much does it cost to operate these bulbs for 8 hours? We need to calculate the total power. It is I delta V. I is 20 amperes and V is 120 volts. So this is 2.4 by 10 to the power 3 watts. Now, the number of bulbs, we divide the total power by the power for one light bulb, 75 watts, so it's 32. So now the total energy, you multiply the power by the time, power 2.4 by 10 to the power 3. And here we have 8 hours for the time. This is just a conversion factor from watt to kilowatt. So it is 19.2 kilowatt hour multiplied by the cost per kilowatt hour. So the total cost would be $2.30. All conductors, if you continue cooling them, you will reduce the number of collisions between the elements. So at one critical temperature, they become superconductor. Superconductor means zero resistance. So the resistance here, it drops to zero. If the resistance is zero, this means the current will be infinite, because the product of resistance current is equal to the voltage difference. If the resistance is zero, then the current is infinity. So for this conductor, you see that at this temperature, like 4.7 Kelvin, at this temperature, it becomes superconductor. But as the temperature increases, the conductor will lose this superconducting behavior. This is a list of the critical temperature for various materials. You see that you need to go down in the temperature in Kelvin in order to have superconducting behavior. However, recently it was possible to mix elements and to create superconductors at higher temperature relatively. Okay. This is just one example of the superconducting behavior, the magnetic floating or magnetic levitation of permanent magnets. Here, because the superconductor has zero resistance, it expels all magnetic field lines from the inside and creates a mirror image for the permanent magnet. Then the image magnet will repel this magnet, and because of the repulsive forces, it floats without touching the magnet. Based on this idea, the new generation of trains can run with very high speed, like 300 miles per hour. In the last couple of years, such train was put into service in China, because simply it's floating top of the rails. It's not touching the rails due to the magnetic force. To have such a strong magnetic field where the whole train will be floating on it, you will need infinite current. You will need high current. And this is what we get at low temperature when the material becomes superconducting. This is a very fascinating field of technology which has many great potentials in the future.